We are almost done with all types of antiderivative techniques. Okay, you've learned kind of the techniques for U substitution. We know how to kind of undo things that, pop up because of the chain rule, so we know how to undo the chain rule. There are other techniques that you don't have to learn, so that's a good thing. Some of them are more complicated than others. But today, we are going to learn how to undo and to take antiderivatives and to come up with like implicit equations. So it's almost, we're going to undo implicit differentiation, okay? But before we do that, let's talk about just differential equations, okay? Because these implicit antiderivatives are going to pop up from differential equations. You'll be asked to solve a differential equation. Differential equation is just some derivative, whether it's dy dx or y prime or f prime, being equal to some function, something. It could be a function, it could be something implicit. And typically, not always, but typically, you will also be given an initial condition. Say y of 1 is 3. Okay, that's a differential equation. It's really just a set of initial conditions. Okay, the solution is the function that meets all of the initial conditions. It's y, or f of x, or something implicit that satisfies the initial conditions. A general solution will just be the antiderivative with the plus c. So if I have that dy dx is equal to 2x plus 3, I could say y or f is equal to x squared plus 3x plus c. It's just really the antiderivative of your differential equation. And the reason why it's general, it's because of the plus c. Shows you that there's an infinite amount of functions or equations that have a derivative that is 2x plus 3. 2x plus 3 can give the slopes of the tangents of any function that looks like x squared plus 3x plus any number. Okay? However, if you are given, say, an initial condition, turns out there's only going to be one possible function whose slopes of the tangents would be defined by this guy and passes through the point 1, 3. So we can go ahead and find c and get our particular solution. 3 is equal to 4 plus c, c is equal to negative 1. And all of a sudden you have a particular solution. No more c. Okay, well, now that we know U substitution, I could ask you to solve this differential equation, which you couldn't have solved until now. But you've been solving differential equations up until now, just with easier things that you can take the antiderivative of. So here's a differential equation. Dy dx is equal to x e to the x squared. Also, y of 0 is equal to 2. Why don't we solve this differential equation? In particular, to solve the differential equation, you know you're finding y. So go ahead and do that. essentially we need to take the antiderivative of this. I see everybody is starting off on the right track here. And we know to take the antiderivative of this, we need to set u equal to that power of e. And we get dy dx is equal to, I don't even need the dy dx, you know. We'll see how we can make it a little more formalized in a second. We'll have x e to the u, replacing dx, I'll have 1 over 2x du. X's cancel. I have the antiderivative of e to the u times a half. Well, that antiderivative is just 1/2 e to the u plus c. Well, that's going to be your y, but of course we can go back and replace the u with x squared. And we now have our general solution. Now we want something more specific because we are given another initial condition. So if this is my general, I can find c by setting 2 equal to this with 0 plugged in for x. Now e to the 0 is 1, so we got 2 equals 1/2 plus c. So subtract a half, you get 3/2 equals c. Y is equal to 1/2 e to the x squared plus 3/2. And now I have a particular solution. Okay, so differential equations, you've been able to solve them. You can still solve them even if they're tougher. Well, what if our differential equations look like this? dy dx equals negative x over y. Well, let's recall some stuff. Let's recall finding slopes of tangents of implicit equations. What were implicit equations? Circles, ellipses, crazy hyperbolas. We even looked at the graph of something that looked like the thing at the back of your throat. Who remembers that? I remember that. We found like the horizontal tangents to that, okay? By taking, the vertical tangents of that. By taking the derivative of an equation that could look like this. 3x squared minus 4y cubed is equal to 8. And this process was called implicit because it's an implicit equation, differentiation. Well, we would take the derivative with respect to x of everything. And what would we get? What's the derivative of 3x squared? Mr. Swisher. 6x. Good start. Mr. Jafrida, what is the derivative of 4y cubed with respect to x?
12y squared dy dx.
Exactly. Good for remembering. When I take the derivative of y, but it's with respect to x, we almost treat it like the chain rule, where we take the derivative of the outside, 6, leave the inside alone, and then the derivative of the inside, for this guy, would be dx dx, the instantaneous change of x over the instantaneous change of x. That's just one. That's why we don't include it here. But over here, the derivative of the outside was 12 inside squared. The derivative of y with respect to x, we say, is dy dx. Okay, so that would equal, what would be on the right side? 0. Good. And then remember, we kind of did some algebraic manipulations, and we solved for dy dx. So I subtract 6x, I divide it by 12y, I'd have x over 2y squared. Cool. We have derivatives of x's and y's. Today, our main focus is on starting here and ending up here. Backwards implicit differentiation. And we will have a technique to help us do backwards implicit diff. And the technique is called separation of variables. It's actually not as hard as you think. You look at this and you're like, oh, how do we go back that way? Just watch. Step 1 for separation of variables is to algebraically move things so that you have your x with your dx's and your y with your dy, or your x's with dx and your y's with dy. I'll say using algebra. Okay, how would that look like for this? Well, I can, move dx by multiplying it by both sides. If you think of this as fractions, which it is. You have dy is equal to negative x over y dx. Well, I can move the y as well, multiplying both sides by y. So we get y dy is equal to negative x dx. Okay, that's step 1. Well, guess where we're going to go from here? We can take the antiderivative of both sides. We have y's that we can take the antiderivative of with respect to y. We have x's we can take the antiderivative of with respect to x. So I'll just say antiderive both sides. That's perfect. So do that. What's the antiderivative of y with respect to y? Anybody? Yes, just 1/2 y squared. It's just like taking the antiderivative of x with respect to x. This would be 1/2 y squared plus a c, right? And over on the right side, we just have negative 1/2 x squared plus a c. Well, the third step is going to be a step that you will skip in the future, and that's to combine our c's onto one side. How do we combine our c's? Well, this is the first constant, this is the second constant. If I wanted to combine them, I could subtract the first constant from the second constant, so that I just have 1/2 y squared is equal to negative 1/2 x squared what would be C2 minus C1? Exactly, it's just another constant, C3. Or you can just say it's C. And these all could have just been C's. Just the key that people forget is that this C minus the C is not 0. It's another C, because you consider these different constants, because the antiderivatives of different functions. Okay? Well, you did it. This is it. This is your general solution. This is an implicit derivative, or an implicit function. If I took the derivative of this, I would get negative x over y. So, not that bad, right? We don't have to be too intimidated as long as we kind of separate things a little bit more. Now, step 4, typically when we go backwards, we are always asked to solve for y. Just because a lot of specific differential equations we'll solve are going to look very, very specific. So we will solve for y. Now I'll solve for y here by multiplying everything by 2. I get y squared is equal to negative x squared plus, what would be 2 times c? Just c. It would be 2c3, but that's just another c. Okay, so we're kind of getting the hang of that. And then I can take the square root of both sides. Just when you take the square root of something squared, you need a plus or minus. All right, I mean, that's it. You take the derivative of that thing, you'd get negative x over y. Or if you graph this, whatever it looks like, it would have slopes of tangents that would be determined by this. Okay? And we'll come back to that one and look at it a little bit more in a second. Let's just do another one. Let's solve another differential equation that is with x's and y's. And I want you to find the general solution in the form y equals f of x. Okay, we should get that. Now, what's important to know is that this is what's asked of you. However, this is just a manipulated form of your solution. Your solution, it really is this. This is an equation. If you take the derivative of this equation implicitly, you would still get this. It's almost tougher to see. If you take the derivative of this, you'd get this, but you would. it's almost like, because it is piecewise, it's actually like even, like, I don't know why we have to solve for y here, but whatever, they're asking us. I feel like the reason why they asked us to solve for y is so we, they make sure we know our algebra good. And I'm talking about the AP test, and the AP test, yeah, that's from a true math teacher. You gotta know your algebra good. Do calculus. All right, let's do another one. Yeah, I don't like how we have to always solve for y, but it's just an extra, an extra couple of steps that they're forcing us to do. Now, we have y prime here. Trying to find y. I don't see a dy or a dx. So do I have to do anything differently? What do you think, Mr. Fig? What was the first thing you did?
Multiply by dx.
Yeah, so you had a dx, right? You just replaced the y prime with dy over dx, right? Okay. So some people get tripped up. They don't know that you can just replace the two, but of course you can. And yeah, multiply both sides by dx, multiply both sides by 3y. Add one, don't subtract one. You took the derivative of root x instead of the antiderivative. Start to crisscross in our brains, especially with u substitution, like, oh, I got to take the derivative and to find an antiderivative, and yeah, it gets confusing for sure. Now, it does. These are great. I mean, we can do it. We can now go backwards. What happened? What? What? I didn't think I said anything funny. Anyways. So we can go backwards. We can reverse our implicit differentiation. But there's actually more that we can see by looking at just this differential equation. Okay? Like, what is great about differential equations is that they give us information about what our solution is going to look like visually without us, even having to solve it. So if I have this differential equation, sure, I found the solution, this, like, I don't know what that looks like. And there's like, doesn't seem to be a way to check to see if this is like correct or not. But there is. Differential equations can show us what we should get. And what I'm leading you to is an introduction to slope fields. Okay, so these are going to be important. I want you to write this differential equation back down, and I want you to create a little XY plane where we are going to produce a slope field. Well, say I don't know how to solve dy dx is equal to negative x over y. I do not know how to reverse the implicit differentiation and find the antiderivative of that. Okay, well, I can use and I can pretend like I know where some of my solution points are. I can kind of say, oh, let's pretend the graph of my solution has the points, y of 1 equals 1. Right? So let's say I have the point 1, 1, and the derivative at that point is defined by this. What would be the slope of my tangent at that point? Negative 1, exactly. So quickly I can just say, all right, dy dx at 1, 1 would be negative 1 over 1, which is negative 1. Well, that's actually information that's going to be kind of helpful, because I don't know what my equation y equals is, and it might not even be y equals. I don't know what it is, but I know that if it has the point 1, 1, the slope of the tangent will be negative 1 like that. Well, before, I could have connected through whatever equation could have been the solution in any which way. Like I say, oh, maybe this is the solution. But now I can't do it like that. Now, all of a sudden, I know, oh, okay, well, maybe we are going to go like this, but I have to pass through like that. Because I know the tangent slope at that point is negative 1. So all of a sudden, I'm getting closer to what my solution looks like. Now I'm just 1 point closer, but it's still a point. Well, let's keep going and let's pretend we have more points that are going to be on my solution. So let's say we have the point 0, 1. Got to get this negative 1 down. Okay. Let's say we have the point 0, 1. Let's say I have y of 0 is equal to 1. What would be the slope of the tangent if I had the point 0, 1 on my y equals solution that has a derivative that's that? 0, right? Good. So dy dx at 0, 1 is going to be negative 0 over 1. That's 0. Well, then I can sketch this tangent. Well, that kind of helps me. Maybe my solution will look like this, but I have to have a horizontal tangent there, and then I have to have a slope that is negative 1 there. Okay, that's narrowing us down. Well, what we can do is we can just keep going and finding more and more slopes of tangents and sketching them, and they will direct us towards what our solution would look like, what our equation will look like. I might not know the equation, but I know what it will look like. So let's look at negative 1, 1. What would be that slope? Plug in negative 1, take the opposite of it, divide it by 1. What do I get? 1. So my tangent slope is going to be like that for a solution. What about at 0, negative 1? I plug in, negative 1, 0. Negative 1, 0. I plug in negative 1, I get 1 divided by 0. What does that equal? That's undefined. Now, what does an undefined tangent slope look like? Yes. That is a vertical tangent. So -1, 0. Now, what about 1, 0? It's going to be the same thing, vertical. And then if I kept going at 0, -1, I'd have a 0 tangent slope. At -1, -1, I'd have a -1 tangent slope. At 1, -1, I'd have a +1 tangent slope. Okay? And I really could keep going. I could say, all right, well, everything on the y-axis, because x is 0, is going to be horizontal. Everything on the x-axis is going to be vertical. Everything on the y equals x-axis will be +1. I'm sorry, that's -1. And everything on the other axis would be that. So these are just all points that I'm saying, let's pretend that that's on a particular solution. What is it going to look like? Well, what is the shape that you can kind of see from looking at this? Like an X, maybe I get rid of the X, or maybe if I filled in the gaps. Yeah, it could be like a hexagon, but let's see if I start drawing, you'd be able to see it. Okay. All right, I'm going to sketch a possible solution by following these lines, right? So if this is true, I'm going to have a solution that on the x-axis is going to be vertical. Well, then it looks like I have to go and have a tangent that's there, but then I have to have a tangent that's 0 when I hit the y-axis. Well, then if I hit 1, 1, I'll hit a tangent that's going to be like that. If I hit the x-axis, I need a vertical tangent. As I keep going down, if I go here, I need that tangent. I need that guy. I need that guy. I need that guy. What do we see? We see a circle. Just what Chris said. Does this make sense? Does it make sense for what we found for the actual solution to this? Let's go back. We already solved this. We already know what the equation is that has a derivative of -x over y. We said it was that. Is that an equation of a circle? I don't know. It doesn't look like it, but you multiply by 2, all of a sudden it looks like this. Instead of solving for y, why don't we add x squared? What do we get? X squared plus y squared is equal to c. That's an equation of a circle. So what we already found, what we didn't know what it was, that was a circle. What we can confirm is that that's correct. This is correct because it follows, these solutions follow the slope field that we were looking at. A circle would have derivatives that follow this. Okay? And what we just produced is a slope field. And if we kept going, what we would have found is this is what more and more tangent slopes being plotted would have looked like. And it's even more and more obvious that the graph of a circle would have tangent slopes that would look like this. So the solution to that differential equation is going to have to be the equation of a circle. Now, what's interesting, though, is, I can have different circles that fall along these slope fields. I can have a circle like right here that kind of falls along with those slopes. But if I go out a little bit more, I can have another circle that has tangent slopes defined over there. I did. I really kind of skipped a couple there. Yeah. Well, Does that mean I have two solutions? Does that mean I have more than one solution? Does that make sense? And why, if it does make sense, does it make sense? Exactly right. We know the solution to this was x squared plus y squared equals c. C is the radius of a circle. I could have any size circle. This could be x squared plus y squared equals 1. This could be x squared plus y squared equals 9. C could be any number, so I have an infinite set of possibilities for the solution, for my original equation that it would have that derivative, negative x over y. Okay, and the slope field shows you that. So what is a slope field? It's really a visual representation. It's a direction field. Yeah, I got fancy there. I go away from it. It's a visual way to see what equation or what graph satisfies the differential equation. Okay? You will be asked to produce slope fields. You'll be given like 6 points and say, sketch the slope field. Now, usually they'll be very specific about the points. You won't have to create something like this. Okay? That's a little excessive. But there will be certain problems where they're going to give you the slope field. Like slope fields like that. And they'll pick a point, say 0, 0, and they'll say, hey, sketch the solution to the differential equation that produces this slope field, and your solution passes through the point 0, 0. What you'd have to do is just let the tangent lines lead your way. And they did it for you already, but you can see, okay, I have tangents that look like this, then I have like a horizontal tangent there, then I have these positive tangents that will bring me to 0, 0, and then I still have these positive tangents, and all of a sudden it kind of trails off. I got a 0 tangent there. We're going here, we're in there. So you'd be asked to do that. And then, you know, if you knew or if it was obvious enough, you could say, oh, this is the equation of sine of 1 over x. I'm not even sure if that's right. I'm just making that up. Probably not. Probably not right at all. But if you knew it, you'd be like, ah, that's going to be something like that. And we'll see something like that in the future with another problem. Okay? So here we go. Here is a slope field produced by some differential equation. dy dx is equal to something. And I want somebody to draw the solution to this differential equation that produces that slope field, and your solution has to pass through 1, 1. Ms. Van der Straten, give me a number between 1 and 11. 7. Yeah, it's you, Mr. Rusher. No. 1, 2, 3, 4, 5, 6, 7. I'm not kidding. Was not kidding at all. Miss McMaster did this last class. I know, you're going to have to adjust and adapt. Yeah, like that. Exactly. That's perfect. That was an added element of difficulty there with that pen. But yeah, you would just kind of let the tangent slopes lead the way. And it's like, okay, my tangent slope has to be like that. Then it has to be like that. Then it's got to be like that. And you know, it just kind of leads you there. Okay? So you can do that. It's not that tough. So long as when you sketch, you know, the tangents along the graph that you just put down, the tangents of your graph are the same as the tangents that are shown in the slope field, which you can see. Okay? Now, another thing we would be asked is to take a slope field and match it with the correct differential equation. Now, I'm going to show you how to do these, and then you'll be able to do it on the next one. You notice that the key is you got to pick out ones that are extreme, like zeros or undefined. And you can't really see it here, but there are a bunch of vertical tangent slopes right here at 0. So I know that at the point 0, 0, dy dx has to be undefined. I know at the point 0, 3, my dy dx has to be undefined. And at the point 0, say -3 or whatever number, dy dx has to be undefined. Which out of those 4 produces that situation? Is it cosine of 2x? Well, I plug in 0. What do I get for cosine of 2 times 0? Is it undefined? No, it's 1. So this one will not produce this slope field. Is it e to the 2x? Typically, whenever there's a multiple choice question or we're a little bit confused, we always go to the most complicated looking one, right? Everybody's like, it's probably going to be this guy. But if I plug in 0, I get e to the 0, which is 1. So that's not true. What's it going to be? 1 over x. I plug in 0, I get 1 over 0 undefined. If I plug in 2, I get 1/2. All of these slopes are 1/2. -2. All these slopes are -1/2. Okay, you try. Do this one. And then we have one more to do. Which of those 4 differential equations will produce that slope field? Look at ones that are obvious. This line of zeros should help you determine which one of these is correct. What'd you get, Ms. Carr? X minus y is correct. 0, 0, slope is 0. 1, 1, slope is 0. 2, 2, slope is 0. 3, 3, slope is 0. Finally, something that could be asked of you is you will be given the slope field and you will be asked which one of these could be a solution rather than which one of these produces this slope field. Okay, look at the slope field. Think about the solution, sketch the solution in your mind that would follow these tangent slopes, and then pick out the correct one. What is it, Ms. Crawford? Take a guess. B. Cosine of x looks like this. Here we go. Cosine of x looks like this. Oops. The pen really is off, huh? Cosine of x looks like this. Does this follow the... Okay, so no. All right, so try again. It's not B. What is it? A, let's see. Sine of x looks like this. Does this follow along with that? Nope. C, let's see. X squared looks like that. Does that follow along? Nope. So what is it? D, because x cubed looks like this. All right, we got it. Good job. We'll see you after the weekend.